check this out. PC, Mac, and they're connected. You guessed it, peer-to-peer. So on this one, I can type hello, and I will send hello from here, and over here I see hello. And when I type hello back on this very clacky keyboard, I get PC saying hello back, and I say, are you a PC? And you get the idea. Today, we're gonna build a CLI-based chat tool using IRO and the Gossip protocol. We wanna sort of walk through this from start to finish. This might be a little long, this might be a little rambling, but I think the nice thing here is at the end of this, you will have a really clear understanding of what it looks like to practically build an app with IRO. Now, IRO is written in Rust. And Rust is going to be new for a lot of you. This is going to be kind of one part tour of Rust, one part tour of IRO, because you're going to need to see some Rust to really get the full breadth of IRO. This is not going to be the 17-hour, here's how the borrow checker works thing. What we're going to do is give you a smattering and a amuse-bouche, a light taste of what it's like to write some Rust. I'm going to give you a bunch of code. You're going to copy and paste it. We'll talk through the bits and what they mean and how they work. You will not leave this tutorial a Rust master, but what you will have done is actually ran and compiled some stuff. You will feel a little less terrified of the language if it is terrifying for you. And for those of you who know Rust, there are chapter markers and you can just skip all the stuff that you already know and you'll get right to the bits that are about distributed systems. First and foremost, we're gonna start with just a new project. And before we even do that, we're gonna do a very basic crash course in getting Rust on your machine and some of the basics of what the Rust ecosystem looks like. So the first thing I'm going to do is I'm going to go to Google and I'm going to type install Rust because that's how I do it. And we go here, we find this thing, and you're going to paste in this piece of code and you're going to hit enter, and it's going to walk you through installing Rust. When this finishes, Rust will be on your machine. It'll be platform specific, you'll be all good, cool. There's a few other things that you should know about kind of as like a way that a Rust developer primes their hands for a project. The biggest of those is called Cargo. Cargo is the package manager for Rust. It does a few other things, but you'll know that Rust was probably installed on your machine if you type cargo and hit enter, and you get output of some kind. As with most things, we're just gonna start with creating a fresh project that has nothing inside of it. We're gonna get to hello world, and then we'll start to build from there. And so we'll use cargo for that. And so the first thing I'm gonna do is make a directory as our starting point. And so I'm going to do makedir mkdir, and I'm going to type makedir IRO gossip CLI. And I'm going to do cd into IRO gossip CLI. And then I'm going to do cargo init. And you'll see it created a binary, in parentheses, application package. And from here we can do cargo run. And what that's going to do is compile and run our program. Cool, all right, let's get an editor out. We're gonna talk through some of the details of what that is. I've gone ahead and opened our directory inside of a text editor. You do really need an editor of some kind. Doesn't matter what you use. You could be a Vim, Emacs, VS Code. I'm using Zed because it's fun and I'm trying new things. And it doesn't really matter. The biggest thing you need is completions. But before we even get into that, let's talk about the basics of the directory structure that we're working with here. This should look somewhat familiar if you're coming from any other compiled language, the cargo.log and cargo.toml. Cargo.toml is your package.json if you're coming from the NPM world. And src is your source, and there's only one file in there, and it's a main function that prints hello world. So when we run this program, you guessed it, hello world. Everything that gets made there is compiled in the target directory, and by default, you're compiling in debug mode. Now that we have compiling and running Rust, yay, we've run our first Rust program. We've printed hello world to the terminal. Let's quickly talk through this just so you have a sense of this main directory, or this main folder. Rust files end in .rs. There is a function main. This is the one that gets called if you're writing a binary. If you're writing a library, there's no main function. When we read it, it printed out with this println thing. A couple of things you should note right out the gate. This exclamation point is a macro. We're not going to talk about those too much, but that's what that is. The exclamation point just invokes some code under the hood, ignoring it. Hello world is a string. Strings are complicated in Rust for reasons that make sense once you read about them. But this prints hello world. Cool. Now that you've run that, great, you run your first Rust program. everything from here should be downhill, right? Now we're gonna need to add some actual crates. Crates are packages or modules, depending on whatever you're coming from in the other languages. But I'm gonna do cargo add to add stuff. And I'm gonna bring in 4 crates to start with. I'm gonna bring in Iro, of course. We're also gonna bring in Tokyo. Tokyo is not Torquio, Tokyo. Tokyo is a runtime. In Rust, you can actually bring different runtimes. That's a whole thing. We're using Tokyo. We're gonna ignore it mostly, but we do need it. So we're gonna do Tokyo. We're gonna do anyhow, which is another crate that lets us ignore more stuff. This is for ignoring errors, or not ignoring, for coalescing errors into a more ergonomic fashion. And we're gonna add rand, which is a source of randomness. You'll see why in a second. So we're gonna add all those. You're gonna see a bunch of GAC here, and then you're gonna see adding and blah, blah, blah. My editor is doing some GAC in the background. And the biggest thing that's changed is our cargo.toml now has those 4 crates associated with them. Your version numbers may be different. If you're watching this deep in the future, good luck. Hopefully it all works. But generally, these numbers are kind of where we're at today. With our crates installed, we're now going to come in and add some code. I'm just going to give you some stuff and we're going to copy and paste it in. If you need any of this, it's all supplied on the website. There will be a link down below to the actual code. And we're going to paste in this, hit save, and then we're going to do cargo run. We're not even going to look at the code. But you'll notice right out the gates, there's some compilation time. Yeah, Rust is a compiled language. You might have to wait a second to compile all this together. Once your cache is warm though, once you've compiled this once, it'll take less time in future compilations. Cool. So after what must have been 17 eons, everything compiled and ran, and it printed out our secret key and our node ID. This is the code that we're going to talk through. From the prior video in our pseudocode, this basically gets us into the same position of setting up an endpoint that we came from later. So if you go back and watch that video, this is now the real code that makes that happen. And you can see how this is kind of the blank canvas starting point that I like to kind of iterate from. And so to talk from the top, both describing the Rust parts and the Iro parts, these use statements that we're seeing up here are the actual way we do imports. So if you're coming from different languages, it's how we import stuff to use it. We can do scoped uses of small little bits and pieces, and it's very common in Rust to only use exactly what you need. Then we have this thing called an attribute. This is a way of modifying code, and we also have noticed that our main function has become async. This modification is just saying, hey, Tokyo runtime, this is the main function. We have to type it. We're going to ignore it. And this result is that part that I alluded to earlier. Anyhow is going to let us ignore a couple of things. These square brackets, this thing basically is the return value of the function. Result is the thing that it's going to return. A result is a thing that can either error or return okay. And the return value that we're going to give as the result is nothing. And so you'll see down here, another funky thing in Rust, the return statements are implicit. So we can type return okay, semicolon. That's fine, we can do that. But by convention in Rust, you just ignore the last semicolon, and whatever the last statement is the return value of the closure. And so here we're saying, okay, return nothing, which means that we're ignoring largely everything. Now for the interesting bits, this is why we needed the rand crate. We are actually generating a secret key right out of the gates to use as the source of randomness as the actual secret key for our endpoint. And here we are not actually using it yet. And so we can do secret key and we can supply secret key. Hey, and when we save that, you will notice my editor automatically formats things. And that's where we should have a quick talk about how you would even get to here in the first place. I didn't just like magically incant all this into existence. You notice that when I went to type this, we have nice editor completions for everything. It's kind of expected for a language like this. But there are some resources on the web you should know about when you're getting into Rust. Crates.io, which is where all the crates are actually registered. So when you do cargo install, it's pulling from crates.io. And this is where you can list stuff. You can even search for stuff like Iro. And hey, there it is. Cool. There's a bunch of downloads and some things. And the other one that's even more important is docs.rs. If you do docs.rs/Iro, it is going to immediately take you to the Rust documentation for that crate. So docs.rs/any crate name, and that's going to give you all the online docs you need. It's also searchable and clickable, and everything's highlighted. It's fantastic. You should use it. And that same documentation is built into the IDE. So when I typed .secretkey here, we're seeing, hey, this is setting the secret key, and then there's references to some stuff. This is very useful. So With our secret key added and our discovery N0 set up, that means we're going to use N0's DNS discovery servers. We are bound to our port. We are awaiting the result of this because this is an asynchronous function that is doing stuff in the background. And then that is going to give us back our endpoint. Once we have our endpoint bound, we print out our node ID and exit the program. And so this program does very little other than go online, figure out that it can talk to the internet, do some like basic hole punching setup, never connect to anybody and close. It's not very interesting, but hey, we can run the program. And honestly, when you're working in Rust, this sort of incremental adding a little bit and then making sure that it executes and compiles, keeping the compiler happy, that's a really nice way to work and the way that I heavily recommend you do work. And so we're gonna build up incrementally from here now that we have what is the basic scaffolding here. We have an endpoint, we have a secret key that has been generated for that endpoint. If in the real world, we can save these or persist them to disk if we want to keep that node identifier around, or we can just generate one on every random process creation as we are here. So with that, let's actually move down to the next step and let's actually get the gossip protocol attached to the endpoint so we can do gossipy stuff. Before we can do anything that uses gossip, we actually need to add the crate. And so we can do that here where we're going to do cargo add iro_gossip. Now with gossip installed, we can move on to actually putting it to use. So more copy pasting. We're going to take this, paste it in, hit save, and I'll get that to compile in the background, cargo run, and we'll talk about it. We're not actually using gossip to do anything interesting yet, but this at least sets us up to do something interesting in the future. So what have we added? We have added the gossip protocol here, which is constructed after our endpoint has been made. And we are passing it a reference to the endpoint so that it can actually dial out. We're going to talk about what gossip does exactly in a second, but this is just kind of the setup that we should understand in the basics. And the next thing we're going to do is we're going to create a router. And a router is a way to accept multiple protocols. It's also just a really nice and fast and convenient mechanism for binding the actual gossip protocol to the endpoint. And then later on, if we want to add more protocols to this program, it's right there and waiting for us. And so here we are registering the gossip ALPN, the application level protocol name, and we are passing it a clone or a copy of the gossip protocol itself. And so this is a gossip instance that we use all the time. We can use that gossip to join or subscribe to tockets. We can actually call methods on the protocol with the gossip protocol instance, and the accept side will be handled through the router. We're then going to shut down the router and wait for that to happen. And once that's shut down, we exit the program. Cool. So when we run this, again, we're going to see that it just executes, prints our node ID, and does nothing else. Because we haven't actually told gossip to do anything interesting yet, but hey, we have a good starting point. So again, incrementally adding up. Now, before we can move on, we should talk about what the hell gossip is and what it's doing. Gossip is based on two big academic papers that we'll talk about in a second. But the thing that it does for you is a message broadcast across an arbitrary swarm of peers. That sounds a little technical. What that means is you can take a bunch of nodes, you can smash them all into the same topic, and then any of those nodes can send a message, and that message will arrive at all the other nodes that are online. And so this is kind of why building a chat room or a chat CLI with this is exactly what we would naturally do, because it sort of models and mimics what gossip is doing already. We have these topics, which we use to sort of isolate different networks. You can think of that as a swarm. And each of those gives you this broadcast channel system that will make sure everything works under the hood. Our gossip implementation has some nice characteristics. All of this is designed to work on a phone. And so we are relying on two critical techniques to make sure that every peer inside of this network has 5 active peers by default, which are basically, think of that as like 5 connections. And then a whole bunch of passive peers that we're just kind of firing and forgetting messages to, usually on the order of like 20. If you think about an average web browser tab, a web browser will have roughly 4 connections to a server at any given moment to parallel grab stuff. That is kind of roughly the same thing as what we're doing here in a gossip swarm. So you can think about this as like 1 browser tab's worth of networking utility. And that has a really nice property. This can scale out to tens of thousands or hundreds of thousands of nodes. And it will naturally handle that scaling characteristic without a coordinating server in the middle. I think it's really cool. It's also quite robust to failing, so nodes can join and leave as they need, and the swarm will ideally hang together. Okay, So we broadcast onto topics. Why don't we start there by actually creating a topic? More copy and paste. So we'll come in here, paste this in, hit save, and run it. And we'll see here, this is going to do the same thing. It's going to print our node and exit. Again, just more incremental building up. But let's get into a little bit of what's happening here below in this topic ID section. In this section, we've added a couple of new use statements. We've added a new use specifically for the topic ID, and that's what allows us to refer to it directly. In Rust, you can actually refer directly to any crate that's available. So I could just as easily do iro gossip proto, which is the protocol, and protocol module topic ID. This is just as valid. And so sometimes you'll see this form, but I think this is a little cleaner. And so we'll do this, we'll come bring back our topic. Cool. So we're creating a topic ID from a set of bytes, and we're using randomness as a source. And so we're just saying, hey, create 32 random bytes. That's going to be our topic identifier. We then have a set of peer identifiers. These are actual other nodes that we want to dial as a set of bootstrap nodes to join this swarm. So the way the gossip protocol works under the hood is you give it at least one peer that is already in the swarm, and you dial that peer to connect to it. And that peer will then in turn hydrate you with the set of other nodes that it knows about, and that will create for you your participation in the network. You might pick up immediately on the bootstrapping problem, which is, hey, we're creating a random topic from nothing here, which means that no one else could know about it, which means that we are the originator of that topic. And this is the origin of a set of roles that we're going to talk about moving forward. In our CLI tool, at the beginning, at some point, somebody has to make the chat room and someone else has to join the chat room. And those are kind of the two roles. You have the creator of the room and then everyone else who joins that room. Any node can take either role. And I think that's the most crucial thing worth knowing. You could at any point say, no, this peer is going to create this chat room, that peer is going to create that chat room. Totally acceptable, right? For now, because we are still not talking to the outside world, we're just building up our capabilities, we're going to pass a vector, which is an array in Rust parlance. That is completely empty. And so we're going to say, hey, we have no peers. We're also going to call gossip.subscribes. This is the first time that we're actually using the gossip protocol directly. So we're taking the instance and we're invoking a method on it to do something. And this is the pattern that we've seen a bunch. We take that gossip instance, we make it, we set up our router, we get everything dialed in, and then we actually start calling methods to do stuff. Here we are then taking the result of that. This question mark thingy that you've been seeing a bunch, what that means is, hey, if there's an error, bail out of the function. Sound good? You can read more about that somewhere else. But we are going to make sure that we are in a non-errored state, and then we are going to call split, which is going to turn this into a tuple. This tuple is going to split into a sender and receiver pieces. This underscore means that we are ignoring the receiver for the minute. We're just declaring it to a variable and doing nothing with it. And with the sender, though, we are then going to use the sender to call broadcast, which means, hey, we're going to broadcast a message to everybody in this swarm of no one, and we're going to send them sup. And from there, we're going to wait for that to finish, and then we're going to shut down. And we're going to move on with our lives. And so when we run this, it executes. And again, it's going to do a little bit of like, hey, how do I get dialed in the background? And then it's just going to exit. Cool. From here, we can actually start to do more interesting stuff. But now we kind of have the baseline, right? The gossip protocol is installed. It is configured. We know how to broadcast messages. We just don't know how to broadcast messages to anyone else. Okay, so that's how messages go out. We broadcast them. How do messages come in, and how do we react to that when they do? Well, for that, we're going to add a subscribe loop where we're going to use that receiver that was an empty variable from before. We're going to put it to good use. So more copy and pasting of code. Let's paste in a bunch of stuff. And this time, before we get going, we're going to encounter some compiler errors. If I go to run this time, I'm going to do cargo run. And this thing is going to get really mad at me. And it's going to give me an actually quite helpful error. It's going to say, hey, two errors are going to show up. The futures light crate is missing, and you need to provide it. And you need that to use this try next thing. Cargo add futures light. And there, with futures light added, we'll do cargo run. And there you have it. It runs. Yay. So what exactly is this futures like crate? Well, if you've ever wondered whether Rust is a systems language and stuff like this is going to just crop up, stuff like this is just going to crop up. The futures like crate enables some very specific feature that we need to be able to read stuff off of an asynchronous stream. It's kind of one of these just like things you got to deal with. And it's not awesome. And this is part of the reason why we're putting you completely on cruise control. Getting your head around how to write this stuff for real and feeling really comfortable takes a while. The upside of taking this approach of just kind of copy and pasting and smashing cargo run is you're going to get a sense of how this kind of works at speed, and that will hopefully give you more patience when you have to grind through compiler errors and understand how Rust is teaching you how to be a better programmer. We're not going to go into too many details on the futures like crate today, but know that it's something that we need, and we're going to use it here, and then we're going to kind of move on. Because the things we do want to talk about are our use of this receiver value. I've written a function for you below called subscribe loop. And it's worth noting this is an asynchronous function that again returns a result of nothing. But what the subscribe loop is going to do is it's going to accept a mutable variable called receiver that is of type gossip receiver. And we have brought in gossip receiver from the IRO gossip protocol. And what this is the actual stream that receives messages. So what this does is we enter a while loop. We then try to destructure the result of the stream, which is saying try next. Hey, keep just trying next, try next, try next. And anytime we get an event out of that, well, anytime we get something, we will process it. If we don't, it'll hit this little question mark and bail out of this thing. And so any error will just nuke this. And so it's not wildly robust, but it works. And then for the inner part here, we are then going to do some more destructuring where we are using match statements, which is this amazing construct inside of Rust that lets you match on types. We're not going to get too much into detail on it today, but this is pulling the event out of and checking to see if it's a gossip event. There are other kinds of events in here. We can do else, just to give you a sense, if event, there is also a lagged event. And this is where we're just going to take a lack and talk about building production grade software is hard. And here we've had to deal with the idea that your machine might not actually be able to keep up with the number of messages being sent to you by the gossip swarm. And there's a place to handle that, and it's right here. We're going to ignore it for this demo code, but when you go to write production code, we have a spot in the crate for you to deal with that. And this is why writing in Rust is worth your time. You're ending up with really robust software that makes you handle a lot of things that you wouldn't think about otherwise. So we're then going to pull apart the gossip event, and we're going to say, hey, is it of the kind where we received a message? And if it did, we're going to print a message that we got. This underbar and then arrow thingy is saying, hey, for all other events, for anything else in this possible set of types, just print out the event that we got. Make sense? This is a subscribe loop, which we are then wiring up via a Tokyo spawn. If you're coming from the Go programming language, this is the rough equivalent of Go do a thing. It's not exactly because coroutines, and there's a whole story and conversation about this, but what this is doing is spawning a subtask that is letting us do some stuff in the background. And so we're then feeding that to the subscribe loop, and we're passing it the receiver. And so what this is setting up is, hey, we're going to subscribe, and we're then going to pass off a thing that will listen for events in a while loop, just constantly processing events as they come in. And then we're going to broadcast as we did before. We're going to send a message. You'll notice when we run this, something that is kind of maybe not intuitively obvious, we did send an event, but we didn't get anything printed out. Gossip under the hood ignores our own events. And that's a process you're going to want to see a lot in peer-to-peer systems. Stuff that you publish out to the network should be handled locally, not in your own event subscription loops. Because you can get into situations where you can say, the kind of natural conclusion is this, hey, someone sent us a message. Maybe we want to dial that person. Well, now you're trying to dial yourself and things are weird. Everything's upside down. It's a bad idea. That is why we don't see the message printed out when we broadcast something immediately. For that kind of stuff, it is worth kind of like digging in on the documentation about this. And if documentation feels unclear, that's why we're an open source project. Jump in and tell us something's unclear, and hopefully someone will modify it to be more clear and things will get better over time. So with that, we are now, just to recap, sending messages. We are subscribing to those messages. We are getting them when they come in. We are still not talking to anyone. And for that, we have this concept of roles, and we now need to figure out a way to get a role to someone else. We won't yet do that, but we'll at least talk through how we signal the existence of our topic ID in our node to some other node. The idea of getting the information about what topic ID and node to join to another machine is called signaling. This is the process of saying, hey, we're going to get this information of how to connect from one device to the other device. Signaling is an out-of-band process traditionally, which sounds kind of weird when we're building apps, right? Just to zoom out for a level, if you're building this into a real app, there's just going to be a server somewhere that has topic ID, a list of chat rooms, and node IDs, list of people to join. And that's how you would set all this up, right? If you wanted this to be completely, fully local without talking to some server, you could use IRO's MDNS discovery to locally discover nodes and just ask them for topics. You would need to build a custom protocol for that, but it's possible to do. These are both and all part of the family of signaling. And for us, I think the most simple for examples and demo purposes of signaling is to use something we call tickets. Tickets is really quite basically just smashing together all the stuff you need into a structure, serializing that into a string, and then passing that ticket around by some means that it supports copy and paste. That usually for me personally is just sending myself a DM on Discord. That could also be QR codes. This could be text messages. This could be anything that supports copying and pasting text. And so for that, we're going to actually implement tickets here, and we're going to print out the ticket to the terminal when we start the service. That's going to give us the first half of signaling. We're actually going to be able to create a token that we can pass to some other machine, and they can use to both assume the join role and then use that ticket to actually perform the join, because they will have the information about the topic ID and the node ID to actually talk to. So more copying and pasting. And this time, this is going to be like fun tour of Rusty stuff that is actually quite useful, because as soon as I paste this in, you're going to see that we are missing a few crates. We're missing something called Serde, S-E-R-D-E, which is a smash up of serialize and deserialize. And we're going to need this thing called data encoding and this thing called Serde underscore JSON. So once again, I'm going to do cargo add Serde, and this time I'm going to use features derive. All of Rust crates support this notion of features. You can actually turn on and off functionality in a crate based on feature flags. It's quite lovely once you get used to it. It does create funny compiler errors when you're like, hey, I installed Serde, but it says that something's missing. It's usually because a feature isn't turned on. So we're going to add Serde. If you want to see the features that are available for a crate, usually they're printed out when you actually install it. They're also on docs.rs. You can read them there. But this says that, hey, I have enabled the derive, Serde derive, and standard features, and allocation, RC, and unstable are disabled. I'm also going to add cargo, add data encoding, and Serde JSON. We're not going to get too in depth on what Serde does, but it's magic. It lets you do these annotations that say serialize and deserialize, and all of a sudden your data structures know how to turn themselves into representations. We then use the Serde JSON crate to actually take those things that support serialize and deserialize and just flip it into and out of JSON. So there is no like to JSON code here. You're seeing this implementation of the ticket information. So this is a struct, and we're then writing methods on that struct. For that, we implement the ticket's direct trait. Traits are a whole thing. We're going to skip a lot of that, but here's another example of a trait. This is implementing display for a ticket, which is relevant because display is what gets used when you print something to the terminal or to the console. And so this is actually how we serialize the entire ticket when we go to print it out. And then this is from string is how we turn a ticket from a string back into a ticket. And again, we're using this the deserialization from bytes methods. So this is kind of dense and looks really complicated. The first time I saw code like this, I was a little like, that's a very obtuse way of saying turn into and out of JSON. There's no to JSON and from JSON method. When you really dig in with Rust, this really feels quite natural over time and is quite elegant once you look at it. For today, we're literally just going to kind of smash this in here and hit enter and talk through it. If you want to Google it more, feel free. But to talk to you about this data structure very quickly, we're creating a ticket type, and we have this topic, which is the topic identifier that we're going to join, and then peers, which is a vector of node addresses. We're smashing those together into a structure. We're then going to print that off. So let's run that out together. And we do cargo run. And while we're doing that, we'll print that out. And hey, this is our ticket. So under the hood, this is some stuff, but let's talk through how we got there. here we're doing the same things we were doing before. We're creating the topic ID, a vector of no one, and then then beneath that, we're creating the actual ticket struct, and then just doing println of it. What's happening under the hood is when we go to put the ticket in the println call, the println macro will check for this formatting display trait that is implemented on that structure, and it will then use that to do a base 32 no padding encoding of ourselves, 2 bytes. It will then turn into a lowercase, and we will write that to the formatter. Kind of neat, huh? So that's how we get the print off. Now we're at a point where we're on the precipice of doing something interesting, because we now have a ticket that we can give to another terminal and use that to instruct it, hey, here's how you join and here's who to dial. And so this is the beginning and the first half of the signaling pattern. Now let's implement the second half. And for that, we're gonna actually have to turn this into a CLI, because from this point, we have not actually had any changes or arguments or inputs that we've needed to accept into this program. And now we'd actually have to do a bit of a sort of detour where we turn this into a CLI tool and then get that to the point where we can then do the roles so that we can say, hey, I want to invoke this as a chat room creator, or I want to invoke this as a chat room joiner. So let's magically turn this into a CLI. So more code, come in, copy, paste, hit save. C, compiler error. All right, we have an error on the crate clap. Clap is another classic of the Cargo ecosystem or the Rust ecosystem. And cargo add clap. And clap is a command line parser, and it shows off some of the, it's a tool for building CLIs. And this is where you're gonna get more of the loveliness of Rust as part of our crash course tour. We're gonna add the derive feature, I think. Yes, clap features derive. We're not even gonna look at the code, let's just run it. Because the output is more appealing now. It's actually gonna look a little more CLI based. And this is, again, more stuff that is not really IRO distributed system stuff, but is really fun because it's nice to see cool tools in Rust, and you might as well have the tour while you're here. But you see now that this prints out like chat over IRO gossip. Where the heck did that come from? If we actually look, this is the argument that we're using, and we're using a bunch of things to derive this as a clap command parser. We can see here clap parser, and this is going to be a structure that parses command line arguments. And the text for this help actually came from the comment above it. And so this attribute actually did some invocation where this triple comment thing does special bits that will then allow the code to use that, the compiler to use that as part of the stuff that gets compiled. And so we can add a bunch of exclamation points here and do cargo run. And magically, a bunch of exclamation points. I'm gonna leave them in. We have a bunch of other bits here. We're not gonna go too much into detail on this, but what this does is it sets up a few things that are worth sort of taking a look at quickly. Here we have the structure that basically declares all of the arguments for the command line. And one of them uses this subcommand derive attribute that will then pass on to an enumeration of 2 different roles, which may remind you of the roles we were describing earlier. You can either open a chat room or you can join one, and you're gonna pass in a ticket. And so when we look at our help text, we have join and we do cargo run, and now we're actually gonna be passing arguments to this. So we're gonna do cargo run join, and this will yell at us because we need a ticket. It was not provided. It is not provided because it is not made optional. This is what optional stuff looks like in Rust. We type option and put the thing that we want to be optional inside of it, and the ticket is not optional. And so clap, the command line parser, says, hey, you need this ticket to be provided as part of the join thing. And so we're naturally getting a whole bunch of behavior that is quite nice and useful. Now that we have our CLI structs in place, our main function changes quite a bit. And the first thing that we're doing before doing any IRO setup stuff now is actually parsing the arguments for our CLI. So now here I have access to args, and this gives us the command and the name, which was part of the global configuration struct, and the no relay, which is here as well. And then on line 50 here, we are doing something called a match, which is we are matching on the command, and we are returning the result of this entire closure into a tuple of topic and peers. So this is all this GAC in here is gonna happen. And then at the end of this, we now have access to topic, which is of type topic ID, and peers, which is a set of node addresses that we want to join. The thing that we're switching on or matching over is the actual type of command. And so this is how we flip between our two roles and decide what to do. In both cases, you're joining a gossip swarm. Only in the open command, we are randomly generating a topic and we have no peers to join. In the join side, we have been given a ticket that we are going to get as a string. We are going to parse that from a string into a real ticket. That will give us a topic and peers. We're then going to print that off so we know what topic we're joining. And we're going to return the topic that we were given and the peers that we were given to the thing that we're going to call later to subscribe and join, which is down here. We then have a little more stuff that we're going to get to in a bit, but we can actually have message types that we can talk about where we're going to build up a richer messaging system for broadcasting, something a little more complex than SUP. And we also have a bunch of code to handle the actual process of connecting and joining. Now, when we run this, specifying the open command, we get a ticket. And here I'm going to, for the sake of ease, create a new terminal and just do cargo run. And then I'm going to type join and I'm paste in the ticket. Hey, we're connected to ourselves locally. Wow, what a magical networking demo. Over here we can type hello. And we got hello over here. And here we can type world. And we got world over here. And so finally, we are doing something exciting and interesting and useful. Yes, we've jumped up a bunch in complexity. We've added some things that I'm frankly just not even going to address in this tutorial, which is how we actually spawn and receive messages from input, where we can actually send input and wire up all that GAC. It's there if you want to look at it. It's not wildly relevant to the actual IRO parts. If it's making a CLI, it's quite useful. The code's right there. For the next bit that I do want to talk about before we leave is the actual message format. So we have this primitive in Gossip where we can now send arbitrary bytes of data. And what we would naturally want to do with that is enrich that into something a little more useful, where this is where we have now message types. And we're going to have two message types in our chat room. We're going to have an about me or a who am I message that's going to say, hey, this node ID has this nickname. And then we're going to have messages, which is going to yield the result of message type, which feels a little funky, but the first one refers to the types of message, and the inner one is an actual chat room message. Hopefully that makes sense. But again, we're going to pass the node ID and the actual text message that we're going to send. What this is going to let us do is we're going to be able to do the same thing that we did with tickets, where we are going to learn how to take that message and serialize it to bytes. Again, we're just going to use JSON here because why not? And we're going to turn those into JSON bytes, and we can come back from bytes. And what this is going to give us is the ability to have a message in our subscribe loop that we had from before. But now what we can do, instead of just printing out the result of the message that we never actually received because we never actually sent ourselves a message, we can do message from bytes, parse it, match over the type, because that's included in the parsing and deserialization, and we can then handle that. And here in our subscribe loop, before anything, we've created a map of names, which maps node identifiers to nicknames. And if we get an about me message, we will insert the node name to the map, and we'll then get this is now known as. And then on the message side, anytime we get it, we're just going to print it out. And we're going to print out the name. If we don't have the name, we're going to do the thumped short of the node identifier, which will give us these short node IDs that we were seeing before. And so this gives you a baseline demonstration of what you can do on top of a Gossip protocol. The baseline thing that you do is just send messages that are of type bytes. Those bytes can be whatever you want. If you want those to be protocol buffers, go for it. If you want them to be straight JSON messages like they are here, go for it. The actual way that you put this protocol into use is totally up to you. What we're giving you is a primitive broadcast system that will work robustly and scale really well. The way that you put that to use is theoretically unlimited. And so just to kind of round out this last demo, we can actually show you how this looks in process, and we can do cargo run. And this time I'm going to pass the name 1, and I'm going to do open. And then on the other one, we're going to quit this and do cargo run. These two little things are to pass flags after cargo run. And again, I'm going to do name. This is going to be 2, and I'm going to type join. And what you'll see here is, hey, we've connected, and we see that is now known as 1. So that message was just automatically broadcast to us as we joined. And we can do hello. And if we go back to our other terminal, hey, this other one is known as 2, and 2 typed hello. So there you have it. That's quite the crash course. I know it's a lot. And what we didn't teach you today is all of Rust. Surprise, surprise. Well, why would we do it this way? First and foremost, hopefully you followed along and actually run some of this from the tutorial page and just copy and pasted and seen this work with your own hands. When you see it work, it's truly magical. The value of writing something this low level in a language like Rust is from here we can get up into far more complex stuff. You can take all of this and compile it for multiple platforms. That's very straightforward. You can compile this for a phone and it'll work. You can compile this with foreign function interface bindings to other languages. By having a really, really, really well-built core in Rust that handles a lot of the low-level networking GAC for you, you have all of the optionality left open to you. This is a form factor that works well across the board. We can get this to run on a phone. This thing consumes very, very, very little in terms of your system resources, and that's a huge upside in working in such a low-level language. Now, generally, you don't need to know all of this sort of in gory detail. As IRO and the surrounding protocols mature, things should look a lot like copy and paste, smash this together, add a little bit of foreign function interface glue to get this into a higher level language, and do more interesting stuff. If you want to see this worked out as a fully fleshed out example, go to the protocols and the gossip thing, and we can actually see in the GitHub repository, everything we've been talking about is one of the examples in the example directory from the IRO gossip protocol itself. The example inside of the IRO gossip protocol crate is even more sophisticated than this one. It takes the extra step with messages of actually signing the messages that are sent over the broadcast channel with the node identifier's private key so that you cannot lie and said node number 2 said this when node number 1 actually created that message and broadcast it. In our toy example, it would be quite trivial to just put the node identifier of somebody else in as the sender of our message, and that would just be accepted by the network. And so this example takes the extra step of giving you a bunch more configuration and shows you how to do signed messages. And so it's well worth having a look. And it's also sort of a nice example of how to run examples themselves inside of Rust crates. So there you have it, a crash course, Rust, distributed systems, peer-to-peer, naturversal, all in one video. What more could you want out of life? I hope you had a lovely day. I hope you enjoyed watching this as much as I enjoyed making it. And yeah, we'll see you somewhere on the internet. Thanks.